I would like to give a quick review before we do our example problem. Okay, so here are our slides. And remember what we're doing is we're water flooding the reservoir, and we're going to focus on a 5-spot pattern. It's the most common of the well patterns. And how well this sweeps the reservoir depends on the mobility ratio. A lower mobility ratio gives higher sweep efficiency. Okay? One way to think of it is that a low mobility ratio means that the oil viscosity is lower compared to the water viscosity. Obviously, relative permeabilities are there as well. At breakthrough, when the water first gets there, you can see that the higher mobility ratio has worse sweep efficiency than this. And as time goes on, the aerial sweep efficiency increases. Eventually, you get to 100% with sweep efficiency, but that doesn't mean you're done producing oil, because you still have 1D displacement efficiency that's occurring on those streamlines. And remember, this is a combination of aerial and displacement efficiency that's producing. If you were to make a plot of oil produced versus water injected, prior to breakthrough, there's the 1-to-1 ratio between the water injected and oil produced, at least if the initial water saturation is equal to the residual water saturation. Then you get to a point where breakthrough happens, and then it starts to taper off. Then you start producing your injected water as well as your oil. And the lower the mobility ratio, the higher ultimate recovery you get. Or I shouldn't say the higher the ultimate recovery, the higher recovery you would get at a finite number of pore volumes. It's got greater sweep efficiency. In theory, it doesn't matter what your mobility ratio is for the ultimate recovery. If you were willing to wait for infinite number of pore volumes or an infinite time, eventually the final amount of oil produced would be the dimensionless oil produced would be SOI minus SOR, right? The only amount of oil you have left is your residual oil saturation. But if the mobility ratio is poor, it's going to take you a really, really, really long time to get there. Okay, so long that it's impractical. This might be a practical amount of time or pore volumes. Okay, so we were looking at a 5-spot pattern, and we were talking about aerial sweep efficiency. We have an injector and producer, and we have these streamlines, and you can think of water going along these streamlines. EA is defined as the swept area divided by the total area. It's a function of the mobility ratio, the dimensionless time, and the pattern. And we're just going to be focusing on a 5-spot pattern here. We're going to define the mobility ratio based on this saturation behind the front. So we got, this is obviously a residual saturation or initial water saturation. This is SWF bar. It's an average saturation. And we had a formula for that on Wednesday for how to calculate that. And you can calculate this mobility ratio as being this ratio of mobilities, right? And so you do it at SWF bar. So we have to find SWF bar and SWI. Okay, so you're going to be given relative permeability curves. You can calculate your relative permeabilities at SWF bar and SWI. You'll know your viscosities, and you can calculate that. If the initial water saturation is immobile, if it was residual saturation, then this term is 0. That makes it a little bit simpler. And again, this SWF bar, we presented a formula to calculate that before, and that all depends on, you calculate SWF from your breakthrough tangent, and then you kind of go from there and do some calculations as I showed. So how do we calculate the aerial displacement efficiency? There are some correlations. And what a correlation really means is that somebody did some experiments and then they fit equations to the results so that we can use them in the future. So this is a plot of breakthrough aerial sweep efficiency versus that mobility ratio. So think the axis is not quite, I think this should be a mobility ratio of 1, not 0.1, but the point is that the maximum is 100, and then it decreases as you increase your mobility ratio. Okay, this is not the aerial sweep efficiency, but the aerial sweep efficiency right at breakthrough. It's effectively this right here, right? This time when it first goes through. So 65% or 83%. You can fit an equation to that, okay? And so you can use this equation and get a number, or you can use the plot directly. You got to be careful because if you're in a mobility ratio lower than here, you can never get a breakthrough aerial sweep efficiency greater than 100. And if you use an MS that's too small, then maybe you get that. So you just need to be careful with that. But this is the equation. You can just plug and chug and get the aerial sweep efficiency at breakthrough. But we want the aerial sweep efficiency not just at breakthrough, but at later times. And an equation, again a correlation that's been fit to data, has been given as this. So the aerial sweep efficiency is equal to the aerial sweep efficiency at breakthrough plus 0.274 times the ln Wi over Wi at breakthrough. So Wi at breakthrough is the amount of water, cumulative amount of water in barrels that you've injected at breakthrough. And then EA is the aerial sweep efficiency at breakthrough. And then if you wanted to find it at a later time, Wi is the amount of water you've injected, so that's going to be greater than WIBT, and you can calculate your aerial sweep efficiency. So we have everything we need, except that, well, we probably need to find a way to calculate the water injected at breakthrough. We're going to make an assumption that along each streamline, the saturation acts like a 1D displacement. If so, the water injected at breakthrough is the sweep efficiency at breakthrough times the pore volume. That's really the pore volume swept. Okay, so parts of the reservoir will be swept with water, part of it won't. This tells you what percent of the reservoir has been swept, or really EABT was the percent, so multiplied by VP, that's the total amount that's been swept. However, and this is very important, in the areas that have been swept, we haven't produced all the oil we can, at least not at breakthrough, right? You would continue to do that. And so the amount, the change in saturation is this average saturation at the front. It was this number here. We had a formula for that. And SWI is the initial water saturation. So now we have everything we need to calculate the aerial sweep efficiency. We got WIBT, we've got EABT, which was calculated, the mobility ratio we calculated, and we can plug it in this formula and get EA. That's not everything we need to calculate the oil recovery. The oil recovery is going to be EA times EI times SOI minus SOR. So we still need to effectively be figuring out how much oil is being recovered in the swept region with time. Okay, and that's really what we're going to do for the rest of these slides. The first thing we're going to do is we're going to calculate the water contacted pore volume. This is effectively a dimensionless time. We were using TD before. The literature uses Q star, at least for two-dimensional flow, and that's super simple. That's really just the water injected at breakthrough divided by the pore volume swept. And that gives you this dimensionless time. What you might want to do is calculate how much water is injected once you get to 100% aerial sweep. So what you do there is you plug in 100% sweep efficiency and you set EA is equal to 1, right? So WI 100 is the amount of water injected when EA is equal to 100% or 1. So you just plug that in. So EA is equal to 1, which is EABT plus 0.274 WI100 divided by WIBT. We already know EABT and WIBT, so we can just do some algebra and solve for WI at 100. Remember, this is the amount of water injected in barrels once we get to 100% sweep efficiency. Okay, so this is the dimensionless time at breakthrough. What about the dimensionless time after breakthrough? And we're going to split it up into two different regions. The first region is from breakthrough all the way to where we get to 100% sweep efficiency. And the second region is after 100% sweep efficiency. So that first region, from breakthrough to WI100, the dimensionless time divided by the dimensionless time at breakthrough, we know that is given by this formula, where A1 and A2 are functions of the areal sweep efficiency at breakthrough and the water injected at breakthrough. EI is the exponential integral function, which you're familiar with. Now, what the TA and I did is we posted a plot of QI star divided by QI star BT versus WI over WIBT at different EABT. That's one of the things that you downloaded from Canvas a few minutes ago. That will be easier than using this formula. Okay, it might be, not perfectly accurate, but it's a nice easy plot. And that there was two plots, and they were just over different ranges of x's. Depending on where you are, one plot might be more useful than the other. If you're injected more water than 100% sweep efficiency, then we have this formula. Okay. Now this one's straightforward, but you do need QI star on 100, which means you need to use this formula to calculate QI star at 100 and then plug it in. Okay, so now that you have QI star, that's the dimensionless time, and we're making this assumption along a streamline, it varies like a one-dimensional displacement. This is going to be very similar to what we did all the way back in chapter 13, 1D displacement, where we took our dimensionless time, we took the inverse of that, and we said that that was the derivative of the fractional flow. So FW prime is 1 over QI star. Okay, so you get FW prime, and you come down and you get the saturation of the producer well. Using the saturation of the producer well, you calculate your fractional flow at the producer well, and our average saturation at the producer well is given by this formula. And then the oil recovery is given by this. Okay. Now this is SWP bar. Okay, it's not SWF bar. SWF bar is a similar formula, but it uses SWF, which is from the breakthrough tangent, FWF, and FWF prime. Okay, so you'll have to calculate both of those things. So with that, are there any questions? Okay. So we'll do an example problem now. We've got about 30 minutes. Let me discuss it briefly. So you have a reservoir that's going to be water flooded with a 5-spot pattern. It's got an area of 10 acres. The reservoir is horizontal. Okay, meaning, what I mean by horizontal, I mean it's sort of flat, so it's not at a dip angle. Has a thickness of 20 feet and a porosity of 15%. The initial water saturation is 0.363, which is considered immobile. So we'll call that the irreducible water saturation. And the residual oil saturation is 0.205. Viscosity of oil and water are 10 in centipoise and 1 centipoise respectively. I suspect that this isn't going to be a particular, this is not, well, it's not going to be a great mobility ratio, right? The oil is more viscous than the water. Okay, could be worse, right? If you had heavy oil in Canada or something, then the viscosity of the oil could be orders of magnitude greater. Formation volume factor, oil and water are 1, and the oil and water relative permeability data are given by these equations. And on the plots, I gave you the relative permeability curves, the fractional flow curve, and the derivative of the fractional flow curve. So, calculate the following by hand. And sorry, I made the first question was this one. Looks like some formatting issue. Let's. I don't think we have time to do full calculations of everything. I'll show you the results, but I don't think we have time to go through everything, and I want to go through everything. So instead, I'll give you some time to think about it, and you can write down the formula or find the equation, and then I'll ask you how you would solve it. You could just explain it to me, and then I'll show you my result. So the pore volume is the bulk volume times the porosity, or the area times the thickness times the porosity. And the area is 10 acres. The thickness is given as 20 feet, and the porosity is 15%. So that's pretty straightforward, except we might need some conversion factors. What conversion factors do you think we need?
You got to convert the acres to feet squared.
That's right. And do you happen to remember what that conversion factor is?
43,560 square feet in an acre.
That's right. And you know, that's something that everybody should kind of have memorized. It's something that you'll use the rest of your life. So that's a good one. That's going to give us the pore volume in cubic feet, so we're going to need in barrels as well. So another conversion factor you should just have memorized is there's 5.61 cubic feet in a barrel. And so I got 232,734 barrels. So maybe after class in your own time, you can verify that you get that answer. But it's just the area times the thickness times the porosity. Okay, now the water saturation at the front, SWF, and the average saturation behind the front, that was our SWF bar, and the average mobility ratio, MS. So you go over to your fractional flow, you draw your tangent line, it intersects right at about 0.6, and that would be SWF. So almost identical to what you had done in previous homeworks and example problems. So that's how we get SWF. And I used a computer to calculate it, and I got 0.596, which was, my number of 0.6 was more than close enough to that. Maybe you got 0.58 or 0.62, and that'd be okay. Okay, but what about SWF bar? How do we calculate that? Right, so here's the formula. SWF bar is average saturation is equal to SWF, which we know. Like you said, you evaluate FWF at that saturation and FWF prime at that saturation, and you plug it in, you get 0.6368. So you all know how to evaluate those. You did it on the exam and in homeworks. So I'll just leave it like that, and you know, you're going to get slightly different numbers than me because you got to read it off the plot, but that's what you get there. And then how would we calculate MS bar now that we know that? So MS bar is this mobility ratio.
That's going to be using that formula that's in the slides, using like the relative permeabilities of oil and water, right?
Yeah. And so the formula is this one right here. So MS bar is this ratio of these mobility sums. Your water and oil viscosity are given in the problem statement, 1 centipoise and 10 centipoise. KRW at SWI is simple. That's just 0, right? We said flow is immobile at initial water saturation, so relative permeability is simple. And KRO is also simple. If you go look at the relative permeability equation or the plot, when your endpoint relative permeability is just 1. It's the coefficient here. So that's 1. The SWF bar is a little bit trickier. Okay. You got to evaluate that at 0.6368. You can either plug it into the equation directly and get a numerical answer, or you could come to the relative permeability plot, and I said, what is it? It's 0.6368, so you'd come up right here and get this value and this value and read it off. Either way, you should get KRW at 0.6368 is around 0.14, and KRO is around 0.07, 0.08. Again, those are those, so you plug it in, and I get a mobility ratio of 1.5. That's not too bad. That's not too bad. So it's not a, this is not a really poor displacement. Viscosity ratio is 10, but because of the relative permeability of water being higher than oil, that or not, you know, that may have had an impact there. So you get 1.5, and then the next question is, any question, just to make sure, so everybody understands how we did all that, right? And I highly encourage you to go through this yourself, especially since we don't have a homework problem on it, and you're going to be tested on the exam in some way on this. So go through it and just make sure you understand that and you get the same answer. So the next thing is that let's calculate the areal sweep efficiency at breakthrough, the water injected at breakthrough, and the water contacted pore volumes at breakthrough. Yeah, so you can use this equation, and I get about 0.62. Okay, and you know, I always like to, an equation like this, it's easy to plug something wrong into your calculator. So I don't know that it's wrong, I don't know that it's right, but what I like to say is I know it's not wrong, meaning that had I gotten a negative number, well, that would be impossible. If I gotten over 100%, that would be impossible. Although we already said that the equation could give you a value over 100%, but that wouldn't be realistic. If the mobility ratio is super low, which it's not, but if it was like 0.1 or something, then the areal sweep efficiency at breakthrough would be 100%. You could also use the plot, and the plot I showed on the PowerPoint notes isn't the best plot to use for that. I might recreate it for you, and that might be easier to use on an exam or something like that. So now that we have the areal sweep efficiency at breakthrough, how do we calculate the amount of water injected in barrels at breakthrough? Right, so it's the pore volume, it's the areal sweep efficiency at a specific time, the breakthrough time. So we know the pore volume, we calculated that. We just calculated the areal sweep efficiency at breakthrough, which is 0.62. In part A, we calculated the SWF bar, which was about 0.6368, and SWI is given in the problem statement as 0.363. So I calculate that we've injected 93,912 barrels at breakthrough. Now the pore volume was 232,000, so significantly less than that. And that makes sense, is that water is going to find its way to the producer before it pushes and sweeps through the whole reservoir. And then what about QI star BT? Okay, that one's simple. That one's just the WIBT divided by VP EABT, or SWF bar minus SWI. And that is 0.2738. And remember what this Q is. It is a dimensionless time. Okay? And so we're going to use it to calculate a dimensionless time at some other time other than at breakthrough. and then we can use it to calculate essentially displacement sweep efficiency. Okay, next question. What is the water injected when the aerial sweep efficiency just reaches 100%? Okay, so we know that the aerial sweep efficiency at breakthrough is 0.62, and water injected at breakthrough is 39,000. But we got to keep on injecting water, and eventually we'll get to 100% aerial sweep efficiency. How much water would we inject at that time?
Thank you.
Yeah, so remember how we did that? We used our EA formula. We set EA equal to 1 and then just did some algebra. But the water injected at 100% breakthrough is the water injected at breakthrough. I'm sorry, at 100% sweep efficiency is water injected at breakthrough, e to the 1 minus EABT divided by 2.274, and I get 156,000 barrels. That sort of makes sense. It's greater than water injected at breakthrough. It has to be, right? It's going to be greater than that. It's also going to be less than the pore volume, and that's because we've left some oil behind when we're doing this. Okay, so the next question. Okay, this one might require a little bit more thinking. What about the oil production and water oil? Well, yeah, don't worry too much about the water-oil ratio, but what is the oil production in barrels when we've injected 50% of the water injected at breakthrough? So this is before water breakthrough, so we haven't produced any water yet, and this is especially true because we're at immobile water saturation. So what that really means is that for every barrel of water we've injected, we've produced a barrel of oil. So we know the water injected at breakthrough. We multiply that by 50%. That's how much water we've injected. And that's how much oil we've injected too. So the water injected is 50% of 39,000, so that's 19,000, and that's the amount of oil we produced. The water-oil ratio is 0, and this is true because and only because we're at irreducible water saturation. So the water that's present is not moving. The next question, this will be the final one, probably today, is what would be the oil production? Don't worry about the water-oil ratio, but what would be the water production at a value that's in between the breakthrough water injected and 100% sweep efficiency? First thing is we need to calculate what WI is, right? And so we know that water injected at breakthrough is 39,000. Water injected at 100% sweep efficiency was 156,000. I asked for the halfway point in that, so that's 98,000. Now, I do not expect to have produced 98,000 barrels of oil because this is after breakthrough and I've started producing some water. So I expect my answer to be less than 98,000. If I get a number that's greater than that, then I probably made a mistake. What I need to do is calculate the aerial sweep efficiency at that water injected, so I use my formula. I've already calculated EABT and WIBT, and now I want WI at 98,000. And so this is an aerial sweep efficiency of 87%. And then what I do is I use this formula. Oh, it's a little ugly, so maybe the easier thing to do is to use that plot I gave you. And there were two plots. And what you need to do is calculate WI over WIBT, which is 98,000 divided by 39,000. And if memory serves me correctly, that's about 2.5. So the one plot goes from 1 to like 50 or something. And so that one might be difficult to use. So we made another plot that's easier to use. And you can evaluate QI star over QI star BT. QI star BT is 0.2738. We already calculated it. And so you get 0.601. Does that make sense to everyone? Okay. Once you've got QI star, then you take the inverse of that, and that gives you your derivative, FWP prime. You go to your derivative plot, right? So your fractional flow derivative plot. From that, you get your saturation, which is 0.6308. From that saturation, you go to your fractional flow plot. You get 1.661. I'm sorry, you get you get 0.94 for the fractional flow, and you plug that into your equations to get SWP bar, and you get NP. NP is EA, which we calculate as 0.8725, SWP bar, which is 0.6669. Initial water saturation is given as 0.363, and we calculated the pore volume to be 232,000, and I produced 61,000 barrels. That number makes sense to me. It's more than the 19,000 we produced at breakthrough, but less than the amount of water we injected at this time. Okay, well, you all have a wonderful weekend.